All right, so in this section, for this video at least, I'm just going to go through what was at the end of section 8.2, which was integrating with respect to y. And this is another method of finding an area between two functions. However, this way works best if we're dealing with something that's not a function. So, for example, if I'm looking for the area between y equals x cubed, which is a function, and x equals y squared minus 2, which is a sideways parabola, so not a function. I could do this by keeping everything with respect to x, because I could say that the x equals y squared minus 2 really is two separate functions, where y would be a positive square root of x plus 2, and y would be the negative square root of x plus 2, which would be the bottom half and the top half of the parabola. And I could graph those on my calculator. And if I did it that way, I would then have to find this intersection, which is at negative 1, and say split my area here. So I could say, well, from negative 2 to negative 1, it would be the top curve, positive square root, minus the negative square root. And then from negative 1 to 1.215, it would be the positive square root minus x cubed. And that's possible. It does require two square roots, however. And so we tend to, if we can, figure out a way to avoid that. Not always possible, but we try. But it is a perfectly okay way to do it. However, what we could do is we could do this with respect to y. WRT just stands for with respect to. And for this, there are several ways to do it. I have the advantage that I can go ahead and just turn my graph to look like this. You could also turn your paper. This is also where I mentioned Emma McDevitt. Uh, if you tilt your head to the right, it then makes the graph look like this. So for our sake, because I am able to turn the graph, I'm going to go ahead and turn it this way so that now y is my independent variable and x is the dependent. I just have to be careful with my y's and that my y-axis horizontally here, the positive y's are to the left, not to the right. Now, if I'm going to do this with respect to y, that means everything is with respect to y. My integral, my bounds, and even my equations. So the blue x equals y squared minus 2 is already written with respect to y, but the y equals x cubed, in order to get it with respect to y, I need to isolate x. So x would be the cube root of y. Well, now looking at this, I see that my cube root of y is always on top of the y squared minus 2. So I can actually now do this area as one integral. The cube root of y is on top, and I'm subtracting all of y squared minus 2, and I'm doing this with respect to y. So my equation, each individual equation is with respect to y, my integrals with respect to y, and then I have to remember my bounds also have to be y's. Now here's where I have to be careful in that my y's are going backwards. So my y's go from this intersection when y is negative 1, moving over to the left until this intersection when y is 1.793. Now I know we could find these antiderivatives. They're not very difficult because they're all power rule backwards. But just to save time here, the integral is then equal to 4.215. And so, again, switching things with respect to y is best when you're dealing with graphs that are not functions. If they are functions, it's not too bad to just leave it all in terms of x. But if it's not functions, it's easier usually to change to with respect to y.